Hello everybody. Today, Alexei Kotov give a talk on geometry through the lens of the differential gradient manifold. Yeah. So we are happy that you arrived on time.
If one can say so. Okay, thank you very much for this opportunity. I will mostly use the presentation file, but maybe I will also write something on the blackboard. So I guess there should be some chalk, right? Okay, there is some chalk, but maybe not that much. Okay, so this talk will be about DG manifolds. Of course, I know that our audience is very prepared, but still, I will repeat briefly some definitions because it's a tradition to do it. And then I will explain how DG manifolds are involved in the description of kind of very general description of equations, symmetries, and deformations. And I will give you some examples. Also, I will explain certain things and announce some papers with some results, which I hope will appear soon. Okay. A DG manifold is a supermanifold, or sometimes it's called a Q manifold. In this talk, I will mix two notations. So DG is more mathematical, Q is more physical, because it was introduced by mathematician Albert Schwarz. So it's a Z-graded supermanifold with a homological degree 1. Homological means odd vector field, which we call the Q field. So it squares to 0 or it's self-commuting. And the category of DG manifolds consists of DG manifolds as objects and graded degree 0 morphisms, which are commuting with Q, and is called Q morphisms. So they're morphisms between two Q manifolds, or DG manifolds. If they are not commuting, if the push forward of one field does not equal to another one, then we can construct what is called the field strength in the notation F. And this is the replacement of the curvature in a more general context. So it measures how much it's not a Q morphism. DG manifolds also form a tensor category, so we can take a product of two DG manifolds as again DG manifold. And the DG submanifold is a graded immersed super submanifold such that the corresponding immersion is a Q morphism. So it means if you restrict the Q field to this submanifold, it will become tangent to it. The internal homomorphisms can be constructed by use of the internal home. Here we use the fact that the category of supermanifolds is not Cartesian, so the home underlined is some auxiliary structure which we can introduce to measure how much it is not Cartesian. And it can be constructed for every two supermanifolds. And if the source manifold has a compact base, it's a free-share supermanifold. Otherwise, there should be some other convenient smooth structure in it. For instance, how's it called? No. Oh my God. It's because of the trip. This smooth diffeology, right? Otherwise, it should be the easiest way to make it into diffeological supermanifold. Okay, so it was my old paper with Giuseppe Bonavolo a long time ago. So the examples of DG manifolds, so the known examples is due to Arkady Weintraub from 1997, that Lie algebroids can be viewed as a Q manifolds of degree 1, and the other way around, every Q manifold of degree 1 gives us a Lie algebroid by use of the derived bracket. And in one direction, the construction is the Chevalier-Eilenberg-Lichnerovich type differential on the differential forms on A, and in the opposite direction, it's given by the derived bracket. So as our audience is very prepared, I don't want to give more details. In particular, Lie algebra and also super Lie algebra with a Chevalier-Eilenberg differential is a Q manifold. And if we take any graded supermanifold and take T shifted by one of it with the Durand operator, the Durand operator can be viewed as a Q field, and it's a Q manifold. Also, Lie infinity algebroids, in my notations, they are non-negatively graded or n-graded DG manifolds. So it's a generalization of a Lie algebroid, like in the Chevalier-Eilenberg direction. But there's also another direction. Well, I will talk about this later. So if L is a Z-graded vector space, we can construct the shift by one, and then view this as a formal manifold with zeros, of formal pointed manifold. And if Q is a formal homological vector field which vanishes at zero, then we call this a formal pointed Q manifold, and those structures are in one-to-one correspondence with L infinity brackets. And then the Taylor expansion of Q gives precisely the brackets. So here it's written as a symmetric bracket from SKV to V shifted by one, but if we shift V back to L, it will be a bracket from lambda K V to lambda K L to L shifted by 2 minus the corresponding degree. In particular, if for 2, it will be of degree 0. So that's what I explained here. And L infinity morphisms are DG morphisms, which are DG morphisms of formal pointed Q manifolds. Actually, L infinity algebra is a particular, in some sense particular, in some sense very general Q manifold. I will show how this appears even in more general context when I will talk about Kaplanov structures and generalizations. So other examples of DG manifolds, the symplectic DG manifolds, where there is a symplectic structure which can be even or odd, and it's invariant under the Q. And in particular, if the symplectic structure has degree 2, then the corresponding DG manifolds are in one-to-one correspondence with Courant algebroids. It's a result of Diemer-Rothenberg. Sometimes also people say Rothenberg-Schivera, because okay. And the group-like objects in the category of DG manifolds are called DG or Q groups. I think once I gave a talk about that. So there is a Lie 3 theory which integrates DG Lie algebras to DG Lie groups, at least in finite degree dimension. And another example is a differential graded resolution of a possibly singular foliation. And this gives a DG manifold which grows in the opposite, in negative, not positive direction. And this is what is called Kashul-Tate resolutions, and there's a nice construction which was explained in particular in the last seminar. It's a construction by Hanchiruk, Laurent Jangou, and Thomas Strobel of the Kashul-Tate resolutions using decorated trees. Actually, we are now in the progress with Sasha Hanchiruk. We are writing a paper about BFV construction involving this sort of resolutions by decorated trees. If you have a bundle in the category of Q manifolds, it's called a Q bundle. So it's a fiberoid bundle in the category of DG manifolds, which is locally trivial as a Z-graded bundle, but not necessarily trivial as a Q. So it's not necessarily true that it's locally a product of Q manifolds. And the DG section is a Q morphism, a section which is a Q morphism at the same time. And so they're very natural example of a DG bundle. If you have a usual fiberoid bundle, we can take T shifted by one of it with the corresponding Q structures, and then the differential of the map is a Q bundle, Q morphism, and we have a Q bundle. And in particular, if it's compatible with a vector bundle structure, then we call it as a DG vector bundle. So it can be nicely described by use of the homogeneity structure, which was introduced by Grabowski and Radkevich a long time ago. So the idea that graded manifolds, in particular vector bundles, which are degree 1 graded manifolds, can be described either by the change of coordinates as usual or by use of some action of a monoid. And this actually it's a very nice structure. In one direction, it's obvious how it works. But in the opposite direction, it was a nice result that one can restore the structure of a positive, non-negatively graded manifold by use of a monoid action. And what I'm doing now with my another collaborator, that we are working on Z-graded manifolds, trying to reproduce a similar Similar idea, but instead of monoid action, there will be some other type of action. In particular, there will be torus actions appear in this context. Okay, so examples of a DG manifold. If you take vector bundles T and shift by K, where K Q filter the total space, it's given by the derivative along Q, and so in particular, the simplest way, any chain complex can be viewed as a DG vector bundle over a point. Now, this structure, which I actually like to explain, if you have a map between two graded manifolds, which is degree preserving, and suppose that both manifolds are also Q manifolds, that we can and this map is not a chain morphism, so it's not a Q map. Then we can produce another map, which is a map from M1 to T shifted by 1 of M2, where T shifted by 1 of M2 is endowed with two Q structures. One is the drum, which always exists. Another is the Lie derivative of the Q structure on M2. And then if you take the total Q structure, which is the sum of two, every graded map from M1 to M2 can be lifted to a DG morphism from M1 to T shifted by 1 of M2. And we call it a generalized Cartan map, and this mapping is involved in the construction of characteristic classes. And why it's a generalized Cartan? Because it's precisely used in the Cartan-Weil construction. Yeah, it was our old paper with Thomas Ströbo about characteristic classes via Q bundles. But in particular, you can just remember that the nice example is just Cherenkov classes, and they appear in this way. Just, but there are some other characteristic classes. For instance, characteristic classes of flat structures, or I think I never published this, but in particular. But I think it's more or less written in the paper of Kontsevich. Also, Razansky-Witten class can be described like this. So I wanted to put it in this framework, but it was also already explained by Kontsevich. And one of the applications of this formula that we can produce the action function for the Alexander Kontsevich Schwarzer-Baronsky sigma model using this generalized Cartan map. It gives some kind of easy construction of it. Okay, so now let me explain a little bit about DG submanifolds. So as I said, if you have a submanifold, graded submanifold of degree, I mean, if it's a graded immersion, then we can call this a DG submanifold if the Q structure is tangent to this submanifold. In general, it's not true. So I draw the picture, right? So this is the picture on the bottom. So blue is a submanifold, and V1, V2, V3. I'm using some kind of even intuition, even geometric intuition, but in super case it's similar. So if you restrict our Q structure to a submanifold, it's not necessarily tangent to it, right? So and I wrote by red those vectors which are not tangent, and by blue the only one which is tangent. If it's always tangent, then it's a Q submanifold, DG submanifold. So. And in particular, it's a simple exercise. Everyone can check it. So if you have a graded submanifold of dimension m cross m inside T shifted by 1 of y with the standard DG structure, which is given by the drum operator, then Q submanifolds are in one-to-one with usual submanifolds of y, and the embedding is given by usual submanifolds x of y, and the embedding is given by the embedding of T1 x, T shifted by 1 of x, into T shifted by 1 of y, by the tangent map to the immersion, to the embedding. And then if it's not of degree m cross m, there can be some other examples. For instance, every involutive distribution can be viewed as a Q submanifold. It's not of that type. But if the dimension even an odd coincide, then it's necessarily of that type. And this is an easy exercise to see why is it so. I really like a few lines of the proof. So there is a one-to-one correspondence between smooth maps between manifolds y1, y2, and Q morphisms from T shifted by y1 to T shifted by 1, y2. And m-dimensional submanifolds x and site y are in one-to-one correspondence with graded Q submanifolds of dimension m cross m of T shifted by 1 of y. And as I said, the letter is given by the inclusion. Okay, so and here is a simple proof. What is less simple is the same for complex manifolds. So for complex manifolds, we also have a Q structure, which is a little bit weird because it's half complex, half real. So we can look at T shifted by T01 to the anti-holomorphic vector bundle of y. So for that, we need to complexify C of y and take the part which is anti-holomorphic. Look at the differential forms of degree 0 Q. This will be viewed as functions on those manifold. And then the Dalbo operator gives a kind of Q structure. So what I'm saying is, why is it weird? Because it's like it's smooth on the base and complex on the tag, but it's not complex analytic. If you can see it's complex analytic, it will vanish. The operator will vanish, of course. Then what is less simple, and actually it was some exercise for me to prove it, that I haven't seen it I haven't seen it in this way in literature. If no one tell me that it's known, then it will be in our paper with Camille Laurent-Jangou, which will follow. And the idea is the following, that there is a one-to-one correspondence between complex submanifolds, complex maps from complex analytic maps from Y1 to Y2 and Q-morphisms from T01 shifted by 1 Y1 to T01 shifted by 1 of Y2. It's actually the easiest part. It's more or less straightforward. But what is less straightforward, there are also DG submanifolds of the corresponding dimension 2K, 2K, real dimension 2K, 2K are in one correspondence with complex analytical submanifolds of Y. So this, actually, for me, it was not completely obvious to prove how to prove it, because the previous simple way does not work. Okay, now I want to examine one of the examples, which is supposed to be the simplest one. Suppose we have a usual Lie algebra. It's even finite dimensional. Fix a basis. If you fix a basis EI, then the structure constants will give you the corresponding Q field. I wrote this explicitly in the dual linear coordinates, right? So it's easy example, everyone knows that. Then Q submanifolds are in one-to-one correspondence with Lie subalgebras of G. Okay, it's also kind of easy. And now I want to look at the following question, and I will illustrate how the deformations will be related to DG manifolds. So suppose we already have some subalgebra, so it's a Q submanifold of the corresponding Q manifold, and I want to describe deformations of it as a Q submanifold. And I want to do this by use of the following. So let me decompose G into the sum of H, which is a subalgebra, plus some complementary subspace, which is not necessarily subalgebra. And then you'll see what happens if A satisfies certain properties. But in general, it's just any vector space complement. And then small deformations of H will be given by graphs of linear maps from H to A. What are the equations for phi such that its graph defines a Lie subalgebra? Okay, so we need to require that if you take any element in the graph, which will be in the form V1 plus phi V1. So V1 belongs to H, phi V1 belongs to A, so it's an element of G. V2 belongs to H, phi of V2 belongs to A, so it's again an element of G, so it's a direct decomposition, unique direct decomposition. If you take the bracket, it should be again in the graph, so it should be in the form V plus phi of V for some V from G. Now let's try to see what will be the equation for phi to satisfy this property. So let's take the bracket. Again, it's again a kind of simple exercise, although usually people don't do this for a general A. But it's not complicated to see that the bracket will be V plus phi of V for some fixed V, which can be defined like that. So it's the bottom line, plus some correction. So, and this correction is looking like that. right? It's pretty long, but I will show you what will this term mean geometrically. So the graph of phi determines a Lie algebra if and only if b equals to 0, right? So because b is the correction, b is the correction, so v plus 1 plus 5v1, v2 plus 5v2 is of the form v plus phi of v is uniquely fixed, it's the bottom line, plus the correction b. But the correction b belongs to A. So and this tells us how much it is not in the graph. If b is 0, that is in the graph, we have a Lie subalgebra. So in general, this equation is cubic, as you can see, right? So the first line consists of 3 linear terms with respect to phi and 1 quadratic. The second line consists of only quadratic terms, and the last one is cubic. So in general, it's a cubic equation with respect to phi. And let's look at the corresponding pieces. I denote them by red, blue, and green. And let's see what happens if those pieces disappear, but not for a particular phi, but for all phis, right? So what happens here? So the red part, the last one, which is the cubic, and it equals to 0 for all phis, if and only if alpha is a Lie subalgebra. So the complement is a Lie subalgebra. So the blue part, okay, suppose red disappears, right? So it's we have the complementary subalgebra, so our G decomposes as H plus A, but we don't know how H and A are connected to each other. So the blue part disappears if A is particularly ideal. So the projection from G to H is a Lie algebra morphism. And in the previous notations, it corresponds to a Q bundle. Okay, so the projection from G to H is a DG bundle. And the additional green part vanishes if A is an abelian ideal. And if the green part vanishes, we will have a linear structure. And it will mean that locally our deformation will be, our Q field will be linearized. And I will say it in a bit more general context slightly later. Now let's try to understand what does it mean geometrically. Again, it's a toy model, and in this case, everything is finite dimensional, so it works pretty well as a toy model explanation of what happens. So as I said, DG submanifolds of dimension m correspond to Lie subalgebras. So let's consider the graded space of submanifolds of a graded dimension 0 m. So and in general, it's not. So I want to make it super. So actually it's a Grassmannian. So I don't want to have just 0 degree invariance. I look at the supermanifold, super Grassmannian subspace, super Grassmannian manifold. And the 0 degree part here will correspond to the base of this, to the bosonic part of this Grassmann manifold. It admits a non-canonical structure of a graded vector bundle over G, which is isomorphic to that. So if you take, so how to, okay, so we have a super manifold of super submanifolds of a graded dimension 0m of G shifted by 1, and there is a bosonic part, 0 degree part, which corresponds really to subspaces. And this, so the supermanifold is, as we know in the smooth category by use of the Bachelor theorem, is always a vector bundle over the 0 degree part. And this vector bundle is isomorphic to that. So it's isomorphic to the sum for J not equal to 0, lambda J eta star cross lambda, where eta is the canonical rank M bundle over the Grassmannian, and lambda is the corresponding quotient. Then the Chevalier-Renberg Q structure on G shifted by 1 generates a Q structure on this supermanifold, such that Lie subalgebras will correspond to points of the 0 locus of Q tilde. Again, it's a very simple example because everything is finite dimensional. You can just see how it works. So we have a supermanifold. It's not enough. It's not sufficient to consider only the Grassmannian, because the Grassmannian is already even. So if you restrict Q to even, it doesn't give you a DG structure. But if you look at that supermanifold, we obtain a Q structure on it. which is induced by the Q structure on G shifted by 1. And then it's a finite dimensional graded DG manifold. And every Lie subalgebra of dimension M of G corresponds to 0 locus point of Q. And this is an example of a more general picture. So if we have a Q manifold, and in general, I say it's Q manifold, it was really a Q manifold before. But in general, it can be something like what one can call a smooth Q space. It can have weird weird differentiable structure like differential, for instance. So it can be really weird, right? Even worse, if you look at space of submanifolds in this. Sometimes it's good, sometimes it's Frichet. Sometimes it's finite dimensional, as in the previous example, but it's rare. And suppose we have a Q structure on this space. So it's a derivation of the space of functions which skews to 0. It's odd degree 1 which squares to 0. And suppose we have a point of the 0 locus of Q. So Q vanishes at that point. Now let's take the tangent to this space, whatever it means, at this point. So it's a vector space. And suppose it's possible to linearize not the Q field around this point, but the neighborhood. Maybe analytical, maybe smooth, but usually it's a formal linearization, right? So it means that we have a 0 point, we linearize the formal neighborhood of this point, identify with the formal neighborhood of the region inside TZM. Then the Q structure, since it's vanished at this point Z, will give you L infinity structure on this vector space. If it's possible to identify it in such a way, in general, it's not possible. For instance, if you can choose local coordinates, then it can be even always done. Then the general Deligne principle says that formal deformations so you get L infinity structure out of it, and the Deligne principle says that formal deformations of points of the 0 locus, if it can try to deform Z, it will correspond to Maurer-Cartan equations in this Lie algebra. And this actually, it's a very rich structure. How it's written here, it looks very simple. But there are a lot of papers which are treating this in particular cases. I will mention some of the results. So, okay, and this is what I call, due to Deligne and also mathematical physicists, so the general picture which behind to that. So you have the space of fields in general, or okay, let's call this fields using physical terminology. So, and there's a Q structure in it, so there are superfields. And then the 0 locus of this Q structure is the solutions to certain type of equations. Then deformations are Maurer-Cartan equations around this point. The infinitesimal symmetries, or there's some called gauge symmetries, they're given by the flows of Q with the bracket of Q with some vector field of degree -1. This is how it generally looks like. And the equivalence of equations, the equivalence of the corresponding DG manifolds. So it's a very general principle which works in many contexts. Then usually one needs to make sense to that in the particular situation. For instance, there can be many examples. So there, for instance, one can treat complex structures in this context, or generalized complex structures, or Dirac structures for a current algebroid. This will all satisfy those. All will fit into those picture. If you have a Q manifold, you can look at submanifolds, super submanifolds of fixed dimension. Then this space is weird. It's very badly organized, but this can be viewed as a Q space itself, such that the Q structure will induce the Q structure here. And then Q submanifolds will correspond to the 0 locus points of this Q field. And the example with Lie algebras was introduced before. And in the case of Lie algebras, it was finite dimensional. Then suppose we have a Q as a bundle so it's equals a bundle Q X inside Y. And suppose there is a projection which such that X is a section of this bundle, then DG manifolds, DG submanifolds can be, okay, so then we can linearize the formal neighborhood of this submanifold by use of the vertical vector fields and some connection. And this in this direction, we are working now with my PhD student in this direction to generalize Kapranov structure. So what is this? I will explain it slightly later. And this is actually a very nice example, and this corresponds to the case where just remember that in this picture for Lie algebras, where the red and blue parts disappear. So they're complementary to a Lie algebra is an ideal. Then deformations will be really looking like Markov equations. Now, this is the example which is called Kapranov structures. And then, okay, so it appears in one of the papers of Kapranov, then it was generalized by Ping Shu, Matthew Stinan, and So, and collaborators and some other people. And then let me maybe, okay, maybe, do I have, yeah, I do. So let me maybe briefly explain what it means, because I think that people, maybe people heard many times what is a Kapranov structure, but the idea was not really explained for in detail. So suppose we have a Q manifold, MQ.
Big as you can.
Isn't not big enough?
Or you in this.
Ah, okay.
Was it just right?
Okay. So sure. Tell me. Yeah, maybe. Okay, maybe. Okay, let me write the biggest possible. Is it okay? Is it okay like this? Is it okay? Do you see it?
Yeah, I think it's fine.
Okay. So suppose we have a Q manifold. So it's a manifold with some Q structure. So let's take two copies of M. Okay. And let's take the diagonal inside it. Okay, so this is the diagonal inside M cross M. And let's take Q as the sum of two copies of Q, which are coming from two copies of M. Okay, so it's obvious that the diagonal is a Q submanifold, of course. Okay. So the diagonal can be also viewed as a graph of the identity map. It's the same description. Okay, now let us choose a connection nabla. So it's a TM connection. Then choose distortion free. Then we can apply the geodesic map to identify, so this is the geodesic map, to identify the formal geodesic map, to identify the formal neighborhood of the zero section inside TM with the formal neighborhood of, okay, like this, so there are many notations for that. So it's a formal neighborhood of diagonal inside M cross M. And this is the exponential, which is simply the geodesic map. Okay, then the Q structure here transfers to the Q structure here by use of this map. So here we have the Q, which is the sum of Q1 plus Q2. So we'll get also Q here. And this Q is uniquely fixed by the two copies, by Q, because there's no other data. But there's also nabla, which is involved here, the torsion-free connection. Okay, and then we have a Q structure here on this space, but also on this space, there are derivations which is simply given, since it's a linear manifold, T shifted by 1 of M has a linear structure, there are derivations which are simply constant derivations along the fibers, like contractions with vector fields. Okay, and we obtain some subalgebra of derivations, and using the Voronov strict, we produce an L infinity structure. So like this, we produce an L infinity structure on sections of Tm. And how does it look like? So if we start, what will be the derivation, the differential, the degree 1 bracket here, the differential, it will be simply the lead derivative with respect to Q. But the next one, so it's easy, we can always produce such a derivation of vector fields. But the bracket will be now less trivial, and this is given by the lead derivative of the connection along Q. And this lead derivative can be viewed as a section of S2 T star M tensor Tm. Right, so the space of connections, the space of torsion-free connections is a defined space associated to this vector bundle, okay, to the or to this space of sections of this vector bundle. So the difference between two connections belongs to that. And then if you take lead derivative along Q, we obtain an element here. And this element will be, so this space is naturally, it meets a natural action of LQ, and this element will be Q closed, but not necessarily Q exact. And the result which we obtain here is called the ATIA class for those people. If this class in the cohomology is non-trivial, so we cannot kill this by adding something to the connection, then it's not possible. So geometrically, it's not possible to find a connection which is compatible with the Q structure, which is preserved the Q structure. And then what one can see here, so if you use the geodesic map, then the quadratic part of the L infinity is precisely that, or maybe up to a constant. It depends how you normalize, plus or minus. And then there are also high brackets, which can be constructed by use of the connection, and then the only what is involved with the connection and Q structure. Basically, naively, it looks like that. So if you have a Q structure vanishing at the point, then we can look at the formal neighborhood, and this gives you L infinity, which is, if you choose some linearization, it's precisely the Taylor expansion of this Q structure. If Q field does not vanish at the point, the Taylor expansion doesn't make much sense. And this is the geometrical way how to make sense to it. We can decompose in two parts. One will be LQ, and another part will be the Taylor expansion by use of the connection. Okay, but this idea is pretty easy geometrically. So we have the space of submanifolds inside M cross M. There is a diagonal which is embedded here, which is a Q submanifold. And what we do here by use of the geodesic map, we can simply transform a little bit this Q submanifold. So this is precisely the picture which I explained before. So the Q submanifolds inside M cross M, this actually graphs of some maps. It's a big Q space. So this particular Q submanifold, which is the identity, is the element of the zero locus. And if we look at the formal neighborhood, then this formal neighborhood will be identified with that. Not with that, it will be identified with sections of Tm. Okay, and the corresponding L infinity structure is precisely the Kaplanov structure. So this is the simple way how to explain what is that. And as you see, it can be generalized in many directions. Even so, it's not a generalization by itself, it's just the way how to view deformations of certain type of I wanted to say equations because it's another direction. If we apply this to in mathematical physics, it will be some linearization of theories of topological, non-topological theories. But in the more general context, it's a way how to linearize the formal neighborhood of a zero locus of a Q field, make it into an infinity structure, look at deformations, solutions to Maurer-Cartan equation. So what we are doing now with my student Valentina, we examine the case where MQ is a Hamiltonian Q field, and here instead of L infinity, we obtain P infinity, but it's a little bit complicated way. So the idea, we follow more or less this procedure, but the result is somewhat more complicated. But there we obtain a P infinity structure on M, which contains all information about Q. That's a sort of Taylor expansion of Q. Another way how to generalize it.
So you call this a BV type correspondence. Maybe you explained it very quickly, but I missed it. So what do you mean by BV type correspondence?
Exactly that.
But can you just
in the
quickly?
BV case, this really happens. So you have a certain BV space of some certain theory. There is a Q field here, and the zero locus corresponds to equations. This motivated by mathematical physics. I just try to use this word in general for a general picture. But if you look, for instance, the AKZ sigma model, you get precisely that, right? So
but what is the correspondence between? I'm kind of missing the context here.
you mean what?
So BV type correspondence, but like if I interpret literally, the word correspondence means from something to something else. So what do you mean?
I mean the following: that certain type of theories, either certain type of geometries or mathematical field theories, can be viewed in this way. So we have some big Q space, such that there's a big Q field, such that zero locus corresponds to solutions to certain type of equations. And symmetries will be given by gauge symmetries, and deformations will be given by Maurer-Cartan. What I want to call the correspondence is that there many cases can be viewed in this context. For instance, Kadeira-Spencer equations for deformations of complex structures, and the same for deformations of generalized complex structures, deformations of Dirac structures, and there are many many examples were constructed like that. For instance, the KZ sigma model, it's constructed like this, but but there are many field theories can be covered by that. For instance, the KZ sigma model covers Poisson sigma model, Chern-Simons, and many generalizations.
It seems to me that the Q manifolds is a kind of an umbrella.
Yes, right. Yes, precisely, right. That's what I want to say. Whenever we can find some description of either geometrical problem or mathematical physics problem in this, we can start this using this huge machinery. For instance, saying that they're equivalent, right? The equivalent and the corresponding DG manifolds are equivalent, and so on.
Yes, so symplectic full manifold is a holomorphic symplectic manifold, right?
Not necessarily. Here.
And the example of
I didn't say holomorphic. I said symplectic Lagrange, but I didn't say holomorphic in this context. It was before.
Full manifold is a holomorphic.
It was another example. It's not what is written here. It was another example. Yes. So if we
symplectic example of symplectic manifold is a holomorphic symplectic manifold. I think I will consider an example of the second status.
Yeah. I think it's another. This can be a mixture of these two. What you're saying.
In symplectic, a holomorphic manifold is corresponding to what in the type of correspondence.
Here is nothing about holomorphic. Here, what I want to say is that if you have a NQ manifold or symplectic Q manifold, then holomorphic. Okay, so it's a generalization of a Kapranov. Okay, not a Kapranov. It's even more general. So if you have a symplectic Q manifold, such that it's symplectic supermanifold, graded supermanifold with a Q structure which is Hamiltonian, then we can look at the same question. We want to characterize Lagrangian submanifolds, which are also Q submanifolds. And then how to characterize them? We use a kind of similar picture. So in this, so those guys actually we also found that, but those guys, Mikhail Kueka and Schnitzer, they published this before us. So and here the idea is also like that. So if you have a big symplectic Q manifold, so it's like this. Q is Hamiltonian, and suppose this is a Lagrangian submanifold. Okay. Then what can we do? So we want to apply the same idea. So we want to linearize the formal neighborhood of this and construct L infinity. But here we can do even more. So there is a famous Weinstein theorem when he was really very young in 71, I guess. He proved that every Lagrange submanifold, a formal neighborhood Okay, he proved this in many contexts, but in this context, the formal neighborhood of a Lagrangian submanifold can be identified with T star of this submanifold. Okay, in some non-canonical way. So this is T star of n. Okay, it's a symplectic, of course, right? And this such that n will correspond to zero section of T star. Okay, and then if it's a Q submanifold, it means our Q field is tangent to that. But in general, it's somewhere, right? And then how to characterize Lagrangian submanifolds which are close to T star n. To n inside T star n. This can be graphs of differentials of some functions. Okay, then we can construct P-infinity structure like that. We can always lift functions from n to T star n. It will be a abelian Poisson subalgebra. Then we apply the Voronov streak, Ted Voronov streak, and construct P-infinity structure on it. And then the deformations of Lagrangian will correspond to Maurer-Cartan equation inside this P-infinity structure. And this is the generalization of, it's an example of linearization picture. And actually what we are doing with Valentina, we just generalize Kapranov exactly in this direction. So this works perfectly well, so the formulas are not easy. Okay, do I still have? Yeah, I have still have some time. Okay, and then this one, so this is the end. This is related to what I'm doing with Camille Ranjangu, still not yet published. The structure of Q bundle can be too hard, and for instance, as in this picture for the algebras, if the red part disappears, then the complement A to H is a subalgebra. And this corresponds to, if the complement is an ideal, it will correspond to Q bundle. If the complement is a subalgebra, it will correspond to the bundle structure such that the fibers are Q submanifolds. It's weaker. But still, one can construct the equations for the deformations of submanifolds. And if Q is linearizable around n, this was the last one where also the green part disappears. Okay, maybe it's well. So there are many examples when one happens, another one doesn't happen. So if you have, for instance, a complex submanifold, then it's not necessarily true that locally. So this corresponds to different cases of a complex submanifolds. So in the smooth case, the usually tubular neighborhood theorem is true, so we can always linearize the neighborhood. In general, for a complex manifold, it's not true. There were hard theorems by Grauert and others in 60s, and they found the conditions when it's true and it's not. But we can play with that. So the linearization means the holomorphic tubular neighborhood will correspond to the case for the algebras where all colored parts disappear. So it means that Q structure, in this case, the Dalbo structure is linearizable in the neighborhood of the submanifold. But there can be two weaker cases. So one case, for instance, we can construct a bundle over the submanifold such that the fibers are complex submanifolds. An example is a twistor space. In the twistor space, we have a bundle by holomorphic submanifolds, but the base is not necessarily a complex manifold itself. For instance, if you take twistor for S4, S4 does not admit any complex structure. But the bundles will be, so it will be a bundle of CP2 over S4. But all the fibers will be equivalent to C1, so they will be CP1, they will be complex submanifolds. But the bundle will be not a complex manifold. And then another case where we have a bundle which is a holomorphic bundle, so we can always construct a holomorphic bundle from some neighborhood of submanifold to the submanifold. Again, it's weaker than holomorphic tubular neighborhood theorem, but it's harder than the case like twistor spaces. And then what we looked at with Camille Ranjangu, we tried to generalize this and see what can we get in a more general case. Suppose we have a Q submanifold inside a Q manifold. So let's look at the ideal of functions vanishing on this submanifold. We call it J. So denoted by A and AK, the algebras of functions on M, and the case neighborhood of n, respectively. So an k is isomorphic to A divided by k plus 1 power of j. So this can be constructed algebraically. And one can see that the quotient of jk by jk plus 1 is isomorphic to sections of sk of nu star, where nu is the holomorphic normal bundle. Is a normal bundle. So it's a dg vector bundle over n. Then we obtain, so the restriction map from k plus 1 to ak gives us the following short exact sequence, right? So the ak plus 1 maps to ak. So ak plus 1 is the quotient of all functions on the big manifold by the ideal to the power k plus 2, and ak the same by the ideal to the power k plus 1. So there's always such a projection, and what we have in the kernel is precisely jk plus 2, jk plus 1 by jk, and this is this one, sk nu star. And then the split is equivalent to a bundle structure from nk to n. And if we have two splittings, suppose one splitting is already chosen. If we have two splitting which coincide modulo jk, then the difference will be linear. It will be degree 0 section of Tn cross sk nu star. And then now we try to ask the question when phi k from A. The section of this bundle corresponds to the choice of a Q bundle structure from the case neighborhood of n inside M to n. So, and this is true if only if this section is a chain map. So, and now we can construct the cocycle, which we call the curvature. Its cohomology does not depend on the choice of prolongation phi k plus 1. And if this cocycle is a coboundary, it's always possible to construct a Q bundle structure from the case neighborhood of n inside M to n. If we can do this for all possible n, we obtain a Q bundle structure, the formal neighborhood of n inside M to n. Okay, I think that's all want to be the same.
Well, thank you very much for your very interesting talk.
So I think I announced a little bit more. I wanted to refer to papers, but they're not yet published, so I just announced the results.
Okay. Is there any question?
Yeah, just so what are these works that we should be looking forward to? There's some reviews, or there are some specific results?
It's already 3 years standing paper with Camille Ranjangu, which is precisely about this path from complex structures to Q manifolds. So we are asking, we're just asking for the question when. So given a Q submanifold, when it's possible to construct Q bundle structure from the formal neighborhood to this Q submanifold. And the weaker, when it's possible to construct a bundle structure such that the fibers are Q submanifolds. And this gives some bench of characteristic classes. What's actually interesting that even if they do not disappear, then it's still possible to construct this sort of secondary characteristic class appears here, but it's another story. And then and this comes exactly from this question about complex submanifolds, where we can construct a bundle, a holomorphic bundle of a neighborhood of some complex submanifold to this submanifold. And in other papers, which 1 or 2, I guess, which will appear as those which are working with Valentina. And I really think that she must explain next time, because I think it's good for her to explain that. And this is the generalization of the Kapranov structures to the Hamiltonian case. It's one, and also to sections of more general Q bundles. Okay, as much as possible, but at least these 2 cases will be treated.
I understand that you have some new construction in complex geometry, but does the difference is
actually they're kind of new, because this picture, how to say, we don't have too many examples where it really works. We have some examples where it works. Yeah, of course, right. Because as I said, for instance, the example of twistor spaces is not new, it's just an illustration, right? So the idea, the following: if you have a twistor, so suppose we have some hyperkähler manifold and consider the twistor space of over it, then it's a complex manifold. and the twister projection, it's a bundle whose fibers are complex submanifolds, but itself it's not a complex complex bundle, because the projection to the base is not a complex analytical map. However, the choice of a section corresponds to the choice of holomorphic section corresponds to the particular choice of a complex structure inside this hyperholomorphic family, because the hyperholomorphic family consists of it's usual three complex structures I, J, K, which satisfy the quaternionic equations, and all in the Kähler case. Actually, it can be constructed in the hyper complex. That's not the metric is not really needed here. So we have three complex structures. They commute as they should commute. All three are complex. So any linear combination with coefficients with squares to 1 is again a complex structure. So we have a bundle whose fibers are S2, because there are three numbers which the sum of squares. One is S2, but moreover, one can construct a complex structure of it. It's the twistor space. And the projection, the fibers of the projection will be CP1. But the base is not a complex manifold, it's hypercomplex. There's no fixed complex structure here. Okay? If we fix some complex structure, it gives a holomorphic section of this bundle. Right? But if you don't fix it, this is not a holomorphic projections. And this is an example of a bundle which is a bundle of one complex manifold over something. The fibers are holomorphic, but the base, the projection is not. And but this example, of course, is known. It's good to have more. And we are looking at like different cases where we have such a structure where all fibers are complex. The next, we have a complex bundle over the complex base, and this base is a complex submanifold. And the third one, where the formal holomorphic tubular neighborhood is satisfied. And all three are different. Like holomorphic tubular neighborhood is a particular case of complex bundle structure, and complex bundle is a particular case of twister-like structures where the fibers are complex, but the projection is not. And for all these three, there are some characteristic classes which are saying where is satisfied or not.
Long time ago.
He did certain things, right? Yeah. Yeah, in some sense, all this was. Yeah, this is a paper. This is a paper from not exactly that, but of course it was motivated by it's the paper from 1997. I think it's called Rozansky-Witten via formal geometry, something like this, right? Of course, the general idea was known to Kontsevich, right? But this is related, but it's a little bit elaborated because we asked certain questions he didn't ask, right? But the idea is. Yeah, many characteristic classes. Yeah, but I cannot say like this. We have characteristic classes which are specific for this kind of problem. I don't know if they give something for characteristic classes. Okay, it's a question, but I cannot answer.
On the published paper, then you analyze your approach is you see Rozansky-Witten and Kontsevich. Do you consider reconsider the result?
No, okay. The question he asked, he answered to this question. It doesn't make sense to. He constructed characteristic classes. So in his characteristic class, example of characteristic classes by Q bundles, which we have. No, it's a little bit different. I don't know. It's a good question whether it's related to classes of some. I think there is some link. There was some. It's a little bit in a different direction, but it was a talk like 2 years ago. It was a talk of Camille Laurent-Jangou at this seminar, and he published a paper with Simon Fisher, where he indeed constructed some classes. He looked at. I'm not sure whether they looked at the classes, and but they looked at the following problem. Suppose we have a foliation, and then let's look at some singular leaf of a foliation, right? Then there's always possible to construct a transversal model which can be analytic or smooth, but in this case, they take a formal model. And then they looked at at the problem of characterizations of formal neighborhoods of foliation with the prescribed formal transversal model. And then I think he used similar ideas, but it's not exactly that. But he was kind of inspired by that. So it's there is some kind of. But this actually it's not well. What I remember that like the local model is always the same. It's just always the product of some transversal. So it's a sort of secondary characteristic classes of the type. But I cannot say too much because there's a paper of them about that. It's somehow related to what we are doing, but not exactly. So we are looking there precisely what we are looking at the problem when we can, given a Q submanifold, we can construct a Q bundle structure of the neighborhood to the submanifold, or whether this Q bundle structure more stricter property, whether it's linearizable, which in the holomorphic case would correspond to tubular complex tubular neighborhood, and less strict whether it's a bundle with Q fibers. And we constructed classes which are responsible for all these questions. But it's how I don't know exactly how is it related to. Can it give anything new about foliations? It's a question. No, I cannot say it now. But maybe, but I don't know.
Is there any more questions? If not, later.
Thank you.